Não faça.
Hi, and good evening, everyone. So I hope my voice is audible and are you able to see the screen?
Yes, yes.
Okay, yes, thanks. Okay, sure, thanks. So we will jump right ahead into the problem. So in this week, all the problems are mostly numerical. So it will be good to solve those problems. So I presume that most of you are already familiar with the conventional diode bridge rectifier, the full bridge rectifier, um, uh, just with and without the capacitive loads and so on. And I think for most of you, the new concept would have been this, that is realizing what is known as a boost PFC converter, correct? That is, so essentially what you have, I mean, you would have gone through the lecture slides anyway, so there's no point repeating it, but just a brief recap is that you have a diode bridge rectifier over here, correct? Followed by a boost converter. So this is your boost stage, boost DC. So the difference that you would see compared to your conventional boost converter is that in a conventional boost converter, you assume that the input voltage is kind of constant, correct? That is, you assume that the input voltage in a conventional converter, in a conventional boost converter, you would see that the input voltage is kind of constant. All right. But over here, what you can understand is that because you are having an AC over here and you have a subsequent diode stage, the voltage VD that you would get is not going to be your conventional flatline DC. Rather, it would still be a DC, but the point is you would be having something like this. So what you are going to see over here is it is still unipolar. That is, it has only one polarity. It doesn't oscillate between positive and negative, but the difference is that um, what you see is the voltage VD would, or the input voltage to your boost stage is essentially going to be a rectified sine wave. Okay, rectified sine wave that would have kind of um, two two semicircles in one cycle. All right. So with this as the input, your inductor acts, and I think you would have already seen it's working. Okay. So what you would have understood is that S1, so note that S1 and S2 are interchanged over here, kind of what you can call as the active switch and the freewheeling switch, correct? So what you would understand is that S1 is responsible for your inductor getting charged up. So what you see is basically when the inductor charges, the current is flowing something like this, correct? So this is how your inductor is going to charge during the positive cycle. Okay. So let me complete. Just a second. Delay solving. All right. Okay. So one thing is for any converter, right? So any DC-DC converter or for that matter, any converter wherein you have to apply inductor voltaic imbalance, right? So what you would want to do is identify what is the path for inductor current during charging and discharging. Okay. So this is a thumb rule that you would want to follow for all DC-DC converters, that identify the inductor current path, IL path, during charging and discharging, right? During charging and discharging. Okay. There can also be cases where you would see that the input voltage over here, the input voltage is having only one polarity, but there can be cases where your input voltage would be bipolar. Okay, we will see that as we go along the course. So in that case, you will identify the inductor path during charging and discharging. during positive polarity of input voltage as well as negative polarity of input voltage. All right. Okay. So what you would see is during inductor charging part. So when your L is charging, correct? When your L is charging, what you basically see is you start from over here. So you go like this through D1. Your S1 is on basically. Okay. You come back through D4 and back to the source. Okay. So just identify the path. And once you know what is the path, you can always find out what is VL. Correct? VL is basically yeah, thanks for hanging around. I think there was some issue at my end and I got logged out. Okay, so I'll just share my screen once again. All right. So when your inductor is charging, what you see is VL is basically all right. Okay, so VL would be basically the rectified value of input, correct? So I'm not sure. So there seems to be some issue at my end due to which I'm getting logged out. Hi, my apologies. I'm not sure exactly what's happening. I'm getting logged out of my Microsoft account every time. Uh, Hope it works out well now. All right. So VL would be mod VD minus, because S1 is on, the voltage at the other end is going to be 0. So it would just be your mod VD, or which is basically Vm sin omega t. Okay. So this is your VL during the D period or the duty period, correct? During the DTS period when S1 is on. All right. And vice versa when S1 is off, right? When S1 is off, basically your L is discharging now, correct? So when your L is discharging, what you would see is, again, remember that inductor is a current stiff element, correct? Inductor is a current stiff element, which means that it cannot change its current direction abruptly. Okay. So some thumb rules again. Inductor is a current stiff element. Current stiff element, which means IL direction remains same. IL direction cannot change its polarity abruptly. So IL direction remains same. Okay. So how do you identify the path? See over here in the figure also they have marked that IL direction is like this. So now S1 is off. Complete the path such that your inductor current direction remains the same. All right. So what you can see is you start from over here, you go like this, and through the load, you come all the way over here, right? And you can understand that this would be completed something like this. Okay. So this is one particular path for the inductor current. Okay. So because L is discharging, um, and you cannot use S1, so this can be one path. So again, what you do is VL is basically again what? So you start from over here on the right hand side, you are having basically V naught. Okay. So it would be minus V naught, and on the left hand side, you are again having your mod VD. Okay. So that is how you identify what is VL during the charging period and what is VL during the discharging period. And after that, I think all of you know the inductor flux balance principle. Inductor flux balance, or some people also call it Volt-second balance. The idea is that in steady state, the flux of the inductor should be same during charging and discharging. Okay, you can understand that if this is not satisfied, if your inductor flux balance is not satisfied, what is going to happen is the flux would go on building up. Okay, inductor flux balance means basically your phi net is 0. Okay, net flux gained by the inductor is 0 or lost by the inductor is 0. So that is your phi charging should be equal to phi discharging. Okay. So during this period, that is during the DTS period, the inductor current rises. Okay. There is a net gain in the inductor flux. But during the 1 minus T period, the inductor current falls, and see that it is falling to actually the same level. Correct? It is falling to the same level. Okay. This and this are same. Okay. This means that the net inductor current is going to remain a constant value. It will not just keep on increasing. So if it happens, what would happen? The inductor would saturate. Okay, you would have learnt about the BH curve, and you would have also learnt that there is a point at which it saturates. Beyond that, you cannot magnetize the inductor. It has already saturated in the BH curve. Okay. Okay, so you should always, so let's say you will operate somewhere over here. You can operate somewhere over here. So there would be a current, correct? I. So B is proportional to voltage, H is proportional to the current. You will be operating at some operating point. You will be operating at some operating point over here. So beyond some point, you would see that you can no longer magnetize the inductor, correct? The B starts to get saturated, right? Beyond this point, the B is getting saturated, but the current increases. Okay, so that means that the inductor is saturated. After that, just the current will keep on increasing. The inductor will not be magnetized. Okay, so you want to operate within the BH curve. So anyway, that's the relevance of your BH curve. But the point that I wanted to mention was that your inductor flux balance principle should be satisfied, or in other words, flux can also be written as volt into second. Your volt second should be balanced. Okay, that means that your VL into T over the entire time period of TS should be 0. Okay, so that is V, let's say V on into T on plus V off into T off should be equal to 0. This is the criteria. Okay, so your volt second should be balanced or your flux should be balanced. Phi on plus phi off should be 0. Net flux is 0. Okay. So we always take care that in any DC-DC converter, this is satisfied. So this is called inductor volt second balance or inductor flux balance principle. So again, we apply this. I presume you would have already studied about this. And again, what you finally get as an expression is that your this is essentially a boost converter, correct? So because it's a boost converter, just know that your V0 by Vn is still going to satisfy V0 by Vn is still going to satisfy 1 by 1 minus d. Okay, this is still going to be satisfied. So from here, because you know that Vn is actually a time varying quantity, it's a time varying signal, correct? Which is going to be mod of Vm sine omega t. You substitute this over here. So you would get that d is basically 1 minus Vm sine omega t divided by V naught. Okay, this is your duty. And what is this duty correspond to? Does it correspond to S2 or S1? You know that duty corresponds to the active device, which is basically S1. So D is for S1. Okay. So obviously, what would be for S2? DS2 would be basically 1 minus DS1. Correct? Just complementary operation. So you just calculate from over here that DS2 is going to be simply Vm sine omega t divided by V naught. Okay, so any doubts so far? This is all just a recap of what you would have already studied. So if you have any doubts, you can let me know now or we will go ahead to the problems. Okay, so one question, with this converter, is bidirectional operation possible? Can we have bidirectional operation? So here you know that the power is basically flowing from the source side or the grid side to the load side, correct? So the power flow is from here, this is your P in and this is your P out. So my question is it possible to feed power to the grid? Can I feed back power to the grid? Is this possible? Can we feed power to the grid?
No, I think.
Why? Yeah, you're right. You're right. Why? Why can't we feed back power?
Because we are using S1 and S2 switches. So I'm not sure, but as per technically, I'm thinking that we can't feed back to the source because it is a single direction, source to R.
So you are telling it cannot be fed back to the source because of S2 and S1.
S1 and S2 switches, yes.
So, okay, so let's, so one person wrote it correct. So that the answer is not because of S1 and S2, it is because of your diode bridge rectifier. So just, we will go back, revisit the basics of power electronics, right? So you would have, so over here S1 and S2 have been represented by generic switches. But what you see is mostly they are realized with MOSFETs. Okay, so they are realized with MOSFETs. So if you use MOSFETs, by the way, this is the symbol for a power MOSFET. So many people use this symbol as well, but this is generally used for signal level MOSFETs. Just a piece of information. So this is for power level MOSFETs, and this is generally used for signal level. So this is also called as NMOS in analog electronics. Anyway, so they don't generally represent the anti-parallel diode, though it should be represented. They don't generally represent because they don't have much to do with it. But in power electronics, you see that this is basically a voltage unidirectional, but current bidirectional device. Okay, so I can have current flow. I can have current flow both from the drain to source as well as the source to drain. Okay, so current can flow like this, that is drain to source, or current can also flow through the diode, something like this. Okay, source to drain. So current bidirectional. That is why over here, if you wanted bidirectionality, this can be used. This entire half bridge can be used. Okay. However, on the other hand, a diode cannot block bidirectional voltage. It cannot conduct bidirectional current. It can only conduct current in one direction, anode to cathode. Okay, so this is voltage and current unidirectional, right? Correct. So it's unidirectional. So the reason this converter is not bidirectional is because of this. Okay, because of the diode bridge rectifier. So people have researched about it because bidirectionality is a very important property. Okay, so generally the application of these converters is on EV onboard chargers. Okay, the application is on electric vehicle onboard chargers. So EV onboard chargers. Just to make you familiar with the ratings. Okay, so generally, yeah, you can replace diodes with SCRs, but yes, that is correct. You can replace diodes with SCRs, but the point is that generally we don't use SCRs for such applications, low power applications. So these EV onboard chargers are, let's say, rated for, this is a single phase, right? This is a single phase over here. So for single phase applications, generally people go for, let's say, 3.3 kilowatt and 400 volts DC bus. So this voltage V0 would be 400 volts. So 400 volts DC, and obviously input would be how much? Your utility supply, 230 volts or 220 volts, whatever. Okay. So this is a very, very common application, 3.3 kilowatt, 230 volts, 400 volts DC. Okay. So this is very commonly employed. The point is that because these are used for EV onboard chargers, people would want bidirectional property. Why? We not only want to feed it from the grid to the EV battery. Let's say I have excess supply in my, or excess charge in my EV battery, and I want to use it to power some loads. Okay. I need not power my entire house from this, but the point is, let's say I want to use it for a local grid. Okay. In that scenario, I should be able to extract power. So bidirectionality is actually very important. Okay. So that is the reason people have started investigating on bridgeless topologies. So this is a bridge-based topology, right? It's a boost PFC. It is based on a diode bridge. So people have started investigating on bridgeless power factor correction topologies. I don't know if it is still there in the entire course curriculum, but yeah, if you are doing some master's level courses or so on, you would definitely learn about bridgeless PFC topologies. Okay, so where it's something like, I'll just draw the circuit diagram. We will see later on if it's there anyway, but this is just for our own understanding. Okay, so one particular changes, they put the inductor instead of having it after the diode bridge, they will put it in the AC side itself. Okay. They will put it in the AC side. They will have MOSFETs. Okay. Oh. That's it. So this is your V in, this is your L. So you would have S1, S2, let's say, oh, S1, what happened? Okay, so you would have your V in, L, S1, S2, S3, S4, and you have your load V0. So the operation of S1, S2, S3, S4 actually gives you this property of power factor correction. We will see its operation later on, but you know that bidirectionality is proper. It's possible with this kind of converters wherein you don't have bridges, you don't have diodes. So all of S1, S2, S3, and S4 are MOSFETs, okay, which can give you bidirectional operation, bidirectional current conduction. Okay. Okay, so this is just for our own understanding. You will learn about these converters later on. So these are called bridgeless topologies because you don't have a diode bridge. All right. Okay. So this was just an introduction, so on. So let me see if there are any doubts or something, or we will go ahead with the problems now. Okay, it's fine. Can we use this converter to make regulated power supply? Yes, people do use. So what people generally do is, see, the point is for a regulated power supply, as you are asking, you would need a constant DC voltage. That's the point, correct? But you understand one thing, there is one limitation. I shouldn't call it a limitation, it's a property of the converter. But anyway, the point is that here you are having 230 volts. So what would be the peak? The peak would be 230 root 2, which is 325 volts. Okay. So what would be V0? So what would be the rough value for V0? So can it go below 325 volts? Or will it be above 325 volts? Will it be equal to 325 volts? What is V0? What can be the value for V0? So V0, yes, it would always be above, correct? It would always be, so generally we have car battery ratings. So it's based on the battery ratings. Again, we want to use it as a charger anyway. So you have 400 volt DC buses are very popular. Okay. So the point is that this always gives only a boost operation. So from the grid side, you are able to get a boost operation. You are able to get 400 volts. But the point is for your application of regulated power supplies, you may need voltages that are lesser than 325 volts, lesser than 400 volts, right? So yeah, it's a good question. So now the point is what?
Can I want to ask you one thing that if I can I use S1 and S2 switches to make it the voltage rating below also below 400?
No, the point is no. The point is that see the inductor over here. So one thing is, see, just we will go back to DC-DC converters. So you are having a half bridge, correct? Okay.
Yes.
So you are having a V in over here, and this is your V0. So it gives you what operation? Buck boost. What operation? This would give you a
Boost.
This can also give me a buck operation, correct?
Oh.
See, let's say S1 is my active switch, S2 is my freewheeling switch. So when S1 is on, you know that the current flows like this. And when S2 is on, the inductor would freewheel. This is a typical buck operation, correct? Now you can also think about it as something like, okay, so let me complete it with voltage sources. So I'm just taking voltage sources over here. Assume that this is V in and this is V out. Okay. So now the point is it all depends on how you modulate the devices. So let's say this is S2 and this is S1 once again. But the point is during the D period, I close S2. Okay. So the because of the switch is closed, the inductor charges, and when it wants to discharge, S2 gets open, so inductor current cannot change its direction. Therefore, it flows like that. But note the direction of inductor current in both cases. Over here, the inductor current is something like this. Correct? And over here, the inductor current is in the opposite direction. Okay. So that defines whether you are able to achieve buck operation or boost operation. Agree? Okay. Agreed or not till this point?
Yeah, agreed.
Okay. So now let's go back to the circuit. We just told that the diode bridge rectifier is unidirectional, right? Then and therefore you know that your current always flows in this direction, correct? Your inductor current is always something like this. So what you're going to see is it is something like this, correct? Inductor current is entering the switch node, entering the midpoint. Again, inductor current is entering the midpoint, which means that you can only get one operation, then that's boost operation.
Boost operation.
All right?
Yes.
Okay. Okay, so one person was asking about the regulated power supply. So the point is what generally people do is they use two-stage topologies. That is you're having the, I'm not drawing the entire converter once again, but the same converter, correct? That is you're having grid voltage over here. So you're having diode bridge rectifier DBR plus boost power factor correction based circuit. So what you get at the output, correct? What you get at the output is a regulated 400 volts. Let's assume that it's going to be 400 volts. Now what you want for your regulated power supply is not 400 volts. Let's say you want something like 72 volts. Okay. Low voltage battery ratings, you would have learned anyway that they can be 12 volts, 24 volts, 28 volts,
Like
48 volts, 72 volts, even 96 volts, and so on. So
like you're
over
telling
here,
more
what
than
you,
the supply voltage.
sorry?
Yeah, more than the supply voltage, more than the VS, right?
Yeah, so here the voltage would be 400 volts, more than supply voltage. So this is your VN. Peak voltage can go till 230 root 2 V peak. So that has been boosted up to 400 volts, but what I wanted is let's say 48 volts. So from 400 volts to 48 volts, people will step down. Okay. So let's say I want 48 volts over here. People can step down. To step down, what operation do you require? You require a buck operation. So you require a buck operation. But the point is people don't use the conventional buck converter directly. Instead, because it's a very high step down, right? You imagine that from 400 volts, you want to go directly to 48 volts. It's a very high step down. Hmm. So your ratio is like almost 1:10, not exactly, but almost 1:10 or 1:9, let's say. So in order to avoid a very high step down, people generally go for isolated DC-DC converters. You will learn about them later on if you haven't. So they will have some transformer isolation. So it would be an isolated DC-DC converter. Okay. So isolated DC-DC converters is what people use. So um, this is how regulated power supplies are obtained. All right. So the reason I have indicated the capacitor over here is that you would have also learned in the lecture slides, the value of this capacitor is pretty large. Okay. C is pretty large. Okay. Why? Why is it pretty large? Can someone tell why the value for C is large? Why should I have a large value of capacitor?
voltage.
Yeah, voltage ripple, but what is a voltage ripple? Is it the, what is the frequency of that voltage ripple that you would want to filter? See, the point is, we were also telling, right? This is a diode bridge rectifier. So that at the output of the diode bridge rectifier, you are getting a
Pulsating DC.
2 omega ripple, right? The frequency is 100 hertz. So you want, and this 100 hertz is eventually carrying forward till the output, correct? So, but I don't want some 100 hertz ripple appearing over my output voltage, 400 volts. I want the 100 hertz ripple to be as small as possible. I want it a flat 400 volt. You wouldn't get a flat 400 volt ideally, I mean, practically, but the point is you want the ripple part to be as small as possible. Okay, so let's say this is 400 volts. I would have something like this. Okay. If you don't put a large value of capacitor, you would be having a large 2 omega ripple, and that's something you don't want. So the value for C is large because to filter 2 omega. 2 omega means what? 2 omega is your 100 hertz ripple that is coming from your grid side to filter 2 omega ripple. Okay. All right. So any doubts so far? Now from this itself, I can tell you two potential research problems. Many people work on these research. This is very very well researched topic. Many people still actively work on this. One question is, how do we reduce the capacitor? How to reduce C? How to reduce C? This is one research topic. Many people work on it. Okay. Secondly, if you see this entire unit, you are having a diode rectifier, you are having a boost PFC, and then you are having an isolated DC-DC converter. Lot of stages, correct? Lot of switches. So you will be having 4 diodes over here, 2 MOSFETs over here, and depending on your topology, you can have again up to 8 switches. So lot of switches. How do we reduce the number of switches? Okay. Or how do we reduce the number of stages? Can we have a single stage that can give me entire thing? That can do the entire thing in a single stage. Can I do that? So these are questions that are being researched about. Okay. Okay. So any doubts so far, or can we go to the problems? We have been discussing just about this for 45 minutes almost. Okay. So then we will go ahead to the problem. Okay, so see the question. A boost PFC converter fed from 230 volt 50 hertz input. So remember that 230 volts is your RMS. Okay, which means your peak is okay. Anyway, we will write it later on. So V peak is 230 root 2 volts. 50 hertz supply input to supply the 3.3 kilowatt load. I was just talking about a standard rating. So they have given that your P out is 3.3 kilowatt. So you're having a boost PFC converter, very standard. The converter is operated with a switching frequency of 70 kilohertz. So switching frequency is 70 kilohertz. Okay. Regulates the output voltage at 400 volts again. So all of these are very standard ratings. 400 volts. The converter is operating in continuous conduction mode. Then calculate the inductance value in microhenry if the allowable peak to peak ripple current is 1.5 amperes. So what is, so your delta IL is, okay, so your delta IL is 1.5 ampere. So delta IL, mind you, it's your peak to peak ripple. So in this, yeah, so the entire thing is your delta IL. Okay, some people like to call it 2 times delta IL, but follow any one convention properly. Okay, so delta L is 1.5 amperes. Then find out what is the L value. All right. Okay. Okay, so if you want, you can also derive what is L value, or if you remember, that is also fine. But in case you guys are trying to remember it, remember that you're trying to remember the formula and you don't know what is the exact formula. Just one thing that you make sure you take care of is that anyway, this doesn't guarantee that your answer is right, but V is L di over dt, so you can understand that L is going to be V into dt by di, or dimensionally, it should be something like voltage divided by some current should be there. Okay, delta I would be the current over here, and then dt would become Fs on the bottom side. Okay, so this should be satisfied dimensionally. Okay, satisfied dimensionally in case you are going to remember the formula, but it would be great if you can derive it itself over there. That's not a big problem. Okay. Okay, so in order to derive the relation, again, the best thing would be to draw the actual circuit. So I'm not drawing the diode bridge rectifier. You know what is the voltage till the diode bridge rectifier, correct? So this is your rectified voltage. Hmm. So this is your DBR voltage. Let's call this VD, right? And after this, you are having the inductor, and then you are having a half bridge, and then V naught. Okay. And what is VD? VD is basically Vm sine omega t under modulus, because it's a rectified value. Okay. What is the direction of current? Direction of current is obviously like this. Okay. So because the direction of current is like this, inductor is a passive element. So current entering is positive, current leaving is negative. That would be the convention I prefer. And this is S1, this is S2. Yeah. Okay. So understand that this is a boost converter. So during D period, S1 is on, that is the bottom device is on. So because S1 is on, inductor charges, correct? So inductor charges, therefore, your VL is simply, because S1 is on, your VL is going to be VD or mod Vm sin omega t. Okay. So this is during the D period. And what about the 1 minus D period? S2 is on, or rather S1 is off. So inductor freewheels. How would it freewheel? It would freewheel to the anti-parallel diode of S2. All right. So it would freewheel through the anti-parallel diode of S2. Therefore, your VL is going to be VD on the left hand side over here. Correct. And on the right hand side, because S2 is on, there is V naught over here. Correct. There is V naught at this point. So your left hand side is going, right hand side is going to be V naught. Okay. So yeah, so VD is basically mod Vm sin omega t, and then you of course have V naught. So this is, so if you have done this, then the answer is done. So you know what is VL during D period, you know what is VL during 1 minus D period. So apply flux balance. Correct. So pi net is 0 or volt second is 0. Correct? So what you see is that VL on into T on plus VL off into T off is 0. Therefore, your VL on is Vm sin omega t. And T on is basically what? What is T on? T on is dTs. And VL off is so VL off is Vd minus V naught or Vm sin omega t minus V naught into 1 minus d Ts is 0. Okay. So if you solve this, what would you get? You can do the big thing or recognize that this is a DC-DC boost converter. This is a boost converter because it's a boost converter. What you eventually end up is that your D is going to be 1 minus Vn by V naught or 1 minus mod Vm sin omega t by V naught. This is your duty, correct? If you solve this, you will eventually end up with this only. The question is for you to calculate what is the inductance value. Okay. Okay. So you can understand that duty is not a single value. It's rather going to vary sinusoidally, or based on this relationship, it would vary in a particular fashion. Okay. Fine. So let me go to the next slide now. Okay. Or we can also continue over here. Okay, so for as far as the L value is concerned, you take any one instance, either D period or 1 minus D period. Okay, for simplicity, let's take the D period itself. So, what is VL on is equal to what? L into delta I divided by T on, correct? So, VL on is basically what? VL on is Vm sin omega t is basically L into delta I and T on is dTs. Okay. So from here, if you rearrange, you are going to get what is L. Okay. So let's go to the next slide. So we were in the D period, correct? So VL is basically mod Vm sin omega t, and this is equal to L into delta I by T on or L into delta I by dTs. Okay. So rearrange both these equations. So you would be getting L is basically Vm sin omega t into dTs divided by delta I. Or you can write Vm sin omega t into d divided by delta I into Fs. Okay. So now the point is, how would you design your inductor? Because your inductor is designed for the peak value, right? So what I would do is Vm into d divided by delta I into Fs. Okay. So Vm is 230 root 2. Okay. And what would be the d value at that point? We will compute what is the d value and delta I into Fs. All right. So just hang on a second. I will bring my calculator. Oh, my screen is getting blurred. Are you able to see my screen or no? Oh, okay. So just hang on a second, then I will log out and log in once again. So now is my screen visible? Oh, okay, okay. Just a second, I will log in once again then. Yeah, is my screen visible now properly?
Still it is blur.
Oh, still it is blurred.
Oh.
You are not able to see anything that's written in my PPT or?
No.
Oh, okay. I think we have faced enough problems today. So I think in the next week I will make sure I have a new device or something so we don't face this issue. But today we have to complete it. Okay, okay.
Hello.
Yeah, hi. So, is it fine at least now? Oh, I don't know from my end why
I
this is happening.
think some internet issue, I think. So because of that, the screen is not loading properly.
But all of you cannot have
Yeah,
internet issues, right?
we are
Or in my side,
no,
you're
no,
telling.
no. From your side, yeah, your side, I'm telling. We are having a proper internet. From your side, the screen is not loading.
See, actually, I'm also connecting from my institute Wi-Fi only. So, just a second, I will just change it to my connection. This is really unfortunate. Um, any improvements or still the same?
Still the same, still the same.
Okay, so we will do one thing then. So do you guys have any Google Meet or any account, Google Meet account or something? I can create a link over there and share the link so that you can join over there. Or or what I can do is I will anyway complete the session because it's mandatory, but I will upload the slides anyway in the Google Drive link. I hope you are able to see the Google Drive link, right? I have uploaded the slides and sorry, I have uploaded the slides for the last week. So in the same Drive link itself, the slides for this week will also be uploaded. So you can see over there as well. Just a second, I will show you where I have uploaded. So when did this issue start? Was it like this from the start itself, or was it like this
It is
just
not from
somewhere
the
in between?
starting. Somewhere
Huh.
like after the problem session started, that
Oh, okay. So you are not able to see my entire screen, is it, or just the
your
um,
screen is visible, but we can't able to see what is exactly like it is showing blur.
Oh, okay. So you're not able to
What
see
and
what I'm
all
showing
we
right now and all.
no, what and all you are opening it, we can't see, but it is not clearly visible. It is
Oh, okay, got it, got
blur.
it, got it. Yeah, got it. Okay, so one thing is that okay, it's like 144 pixels. I'm really sorry this happened. So from the start itself, I have been facing issues with this Microsoft joining today. I mean, I got logged out 2-3 times, but uh, can you open this Google Drive link? In that, I think you can see the week 1 lecture slide.
It is asking access, and you provide access to us.
I think okay, just a second. I will share. Okay, so anyone with the link can open, correct? Done. Yeah, so now can you check once?
Still it is asking unable to request access.
I have just a second, it's still updating. Yeah, so now I think it would be coming for now you can just reload once
Yeah,
and see.
we can see it. Yeah, it is coming.
Yeah, so this is for week 1, okay? So Like this,
Like
I
it
will
is
do for
showing
week 2 also. In that, I will
proper PDF is not uploaded. Karka, it is showing.
no, I have uploaded this as a PPT.
It is showing as a PDF file. Yeah, it is coming. Week 1, it is coming.
Okay, okay. So yeah, I have uploaded this as a PPT only. Okay. Okay, so I will anyway upload the week 2 slides also over here itself. So from here itself, you can see week 2 slides. So for now, I would have to continue here only because we don't have I don't have an alternate device with me right now. But yeah, you can see week 2 slides uploaded from there. Or one more thing we can do is right now I can upload the slides so that you can see the questions, but I will be solving it eventually and uploading it. So I will also upload the slides. Just hang on a second. I will upload all these slides over there. So please just tell me if you are able to upload if you're able to see the slides. Okay. So if that is fine, then I will just solve it and then update the slides. Okay. Yeah, so can someone please confirm if you are able to see week 2 slides I have uploaded in the drive?
Yeah, it is coming.
Yeah, so I have the questions over there. So if you know already all the answers to the questions, you can please see it. You can go through it. Anyway, I will solve the numerical problems, but since you're all online, we will just discuss. You can also open the slides in your respective computers. We will discuss um, the problems which are not numerical, and the numerical ones I will solve it and then re-upload it. Okay. Or you can also solve it by yourself, but anyway, I will solve it and re-upload. Okay.
Yeah, okay, sure.
Okay. So please go to question number 3. So yeah. So question number 3 is, what will be the peak repetitive reverse voltage of diode in case of single phase full bridge rectifier? So can anyone tell the answer? In case of a single phase full bridge rectifier, what will be the peak repetitive voltage? What is the voltage that the diode has to block basically?
Reverse
Will it be,
voltage.
yeah, so will it be the peak voltage? Will it be peak voltage by 2, peak voltage by root 2, or twice the peak voltage? What is the answer? So we are in question number 3 of the uploaded PPT week 2 in the drive link. Okay, so you please open that. We will see the questions that are non-numerical, and the numerical ones I will solve it and upload. Okay, and before the next week, I think I would have to change my device or something. Right now in this laptop, it isn't proper and I don't have any other device with me right now. Anyway, so yeah, so the answer is option A. The peak voltage that the diode
Yes.
block is, peak voltage that the device would block is basically Vs peak. Okay. Okay. So we will go to the next question. Please go to question number 4. So you can open the PPT itself. So if you're not able to see my screen. So for the single phase full bridge rectifier without the capacitor filter, match the following quantities correctly. Okay. So basically they are asking what is the IRMS of diode and I average of diodes. Okay, so you have got multiple options over here and you have to match. Okay, so now the following, now the point is you can either derive it in the exam, or if you already know the answer, you can go ahead and do it. Okay, so you know the basic definition for RMS and average, right? So from that, you have to first draw your draw how the switch currents would look like, and from that you can find out. So in my screen, I mean, anyway, my screen is not visible to you, but anyway, in my screen, I have drawn the waveform for the switch and the diode are drawn. So from this only, you have to integrate for the time period for which the device is on. From that, you have to find out what is the RMS value and the average value. Anyway, I will upload the derivation in the answers. But for people who already know the formula, the option is B. That is, IRMS of diode is Vs peak by 2RL, and the I average of diode is Vs peak by pi RL. Okay, option B. All right. So this is for single phase full bridge rectifier. Okay. Fine. So next question, again, this is an interesting question. For the single phase boost PFC converter, what will be the variation? So is this fine? Question number 3 and 4. Any doubts? If you have any doubts, like I can try to explain, or I will upload the full answer version in the drive. Okay. Oh, now it's clear. So can you please confirm if it is? Huh?
No, it is not clear. Not clear, not clear.
Okay. Yeah. I'm not sure why this is happening. Okay. Questions all right. Okay. Okay, so we will go to question number 5. That is for the single phase boost POC converter. What will be the variation of the duty ratio for switch S1? Okay, so switch S1 is basically this. That is the lower device. Okay, so S1 is the active device or the lower device, whatever you want to call it. How would the duty vary? So point is, you know the formula for duty, right? So this is a boost converter. So duty is going to be basically 1 minus V in by V naught. So V in is mod of Vm sin omega t, rectified version. So 1 minus mod of Vm sin omega t divided by V naught. Okay. So Vm sin omega t is rectified version. So 1 minus that answer by V naught is your answer. Correct? So what is the answer? Anyone? So what is the answer for question number 5? How would the duty vary? Yeah, so you're correct. So the option is C, because you understand that. Yeah, so because you understand that mod of Vm sin omega t would vary from 0 to Vm and back to 0. Okay. So if you do 1 minus of that, you can understand that the peak value can go till 1. Okay, the peak value can go till 1. Okay, and you are having a repetitive version every half of line cycle. So the same pattern would repeat every half of line cycle. So just for your knowledge only. So are you able to see options A and D? Are you able to see options A and D? So option C and D are how the duty would vary if, let's say, I showed you the initial circuit, right? That is, I showed you a circuit called bridgeless PFC converter where you don't have a diode bridge. Okay, if you don't have a diode bridge, there is no question of rectification and all. Okay, you don't have a question of rectification if there is no diode bridge. Okay, in that scenario, you can understand just intuitively, you can understand that because there is no rectification, because there is no diode bridge. In that scenario, it's just a trivia. Okay, you will learn about it when you learn the converter. But the point is option C and D are relevant if you don't have a diode bridge. Okay, here we are having a diode bridge which rectifies stuff, and that's why you get option C. Okay, option A and D are also valid, but they are for a different converter. Okay. Anyway, so this is for single phase for switch S1. So what about switch S2? Go to question number 6, everyone. For the single phase boost PFC converter, what will be the variation of duty ratio for switch S2? Okay, S1 and S2 are complementary to each other in single phase boost PFC converter. Okay. So any answer? How would switch S2 vary? S2 is your complementary device. So how would S2 vary? Yeah, you're correct. So the option is B. Yes. Why? Because this is a complementary device. If you know what is the variation of S1, 1 minus that is going to be your S2, correct? So 1 minus DS1 would be DS2. Or in other terms, the duty for this device would be directly mod of Vm sin omega t by V naught. Because mod of Vm sin omega t is a rectified sine wave, the duty for S1 would also, for S2 would also be a rectified sine wave. Okay. So again, this is a very common question, by the way. Question number 5 and 6, they are very common. So be prepared for such questions. If you will also learn about the converters where you get options A and D. Okay, so just try to understand where you have to use option C, option B, option A, and option D. Okay, it depends on the converter and what is the switch position, S1, S2, and so on. Okay, so we will go to question number 7. Okay, please go to question number 7. In a full bridge rectifier, with a capacitor filter, there is a capacitor filter, increasing the value of filter capacitor without changing other things like operation, input voltage, and so on. So what could happen if you increase the value of input capacitor filter? So if you increase C, does it decrease the peak current through the diodes? Or diode currents will not change, increases the peak current through the diodes, changes the shape of diode currents but will not change the peak value. Okay. So what would happen to the diode bridge rectifier current? So does the peak current decrease? Will the peak current increase? Or will the diode current does not change or would not change? Or it changes the shape of diode current but it will not change the peak value. So what is the option? Answer, anyone? Okay, so option A is decreases the peak current through the diodes. So why would it decrease the peak current through the diode? You can type, no problem. So what would happen? So everyone please see question number 7. So if you increase the value of filter capacitor, what would happen? Yeah, so option C is it increases the peak current through the diodes. Why would it increase the peak current through the diodes? If you increase your value of filter capacitor, why would it increase the peak current through the diodes? Yeah, so we have got all options today. So diode current will not change. So why can the three of you just in single line, like, or if you want, you can type elaborate answer as well. Why do you feel? Now my screen is clear. So does everyone feel my screen is clear now? Please, can anyone else type in if my screen is clear? If a few of you feel my screen is clear, we can solve the problems. Yeah, and also why do you feel what would happen to the diode current and why? Why do you feel the answer is A or C or B? No takers for D anyway. Okay, so everyone feels the screen is clear. Larger filter capacitance discharges less. Okay, so okay, we will go back. So I think the screen is clear right now. Okay. A few people left probably. I don't know why, what happened. So anyway, so in the answer key, they have given that the answer is increases the peak current through the diodes. Okay, but we will see this question later on. So because we have got some limited time, let's solve the numerical problems first. Okay, so we were there in the first problem, that is a boost PFC converter fed from 230 volt 50 hertz input supplies a 3.3 kilowatt load. The converter is operated at a switching frequency of 70 kilohertz, regulates the voltage at 400 volts. So go to the first problem. Okay, so calculate the inductance value in microhenry if the allowable peak to peak current ripple is 1.5 amperes. So you list out what is known basically. V peak is known. 230 root 2 volts. The output power is 3.3 kilowatt. Assume a lossless case. So your power level is kind of constant everywhere, correct? Okay. And the switching frequency is 70 kilohertz. V naught is 400 volts. Delta IL is 1.5 amperes. Okay. So what is the philosophy, right? So the point is that you see over here the duty is varying continuously. It's a time variant quantity and your input voltage is also varying. So at what point would you design your inductor? Okay. So yeah, so we were over here, correct? Yeah, okay. So I think we are good to go again, thankfully. Okay. So the question is, at what point would you design your inductor so that so we have to design anyway for the worst case, correct? So at what point would you design your inductor? So L L design for worst case. Worst case of what? Worst case of, is it for the worst case of current or worst case of voltage or what? Right? So that's the question. So now the point is you can understand how would the inductor current vary. Your inductor current is going to vary something like this in an average sense. But actually what you're going to see is, let me draw it properly. Okay. So this is how the inductor current varies. But because of the ripple component that you consider, you would be having a ripple component, something like this. Correct? So this would be your ripple component. So obviously you will design for the worst case. right? And worst case refers to this particular operating point where your inductor current is at its peak. Okay, this is your I peak. Okay, so you design your inductor for this particular operating point. Okay, that is your inductor current achieves its peak value. Okay, fine. So what would be IL? So IL is basically what? So I is basically P by V, correct? So I is just P by V. So from this point, if I want to derive, so if my IL has to be peak value, if IL has to be peak, you understand that the term in the denominator has to be minimum. Okay. So if your IL has to be peak value, your voltage should be minimum. Okay. So if I write it properly, so your inductance would be P naught divided by V input minimum. What is the voltage? So what is this voltage? Is it the RMS? Is it the peak value? So what is the voltage? Is it the RMS we are talking about, or is it the peak value? RMS. Okay, so one thing I would like to mention, so there is a reason why I wrote this minimum over here. So the point is, in this question, they have given just a single value, correct? They have given just 230 volts. Okay. So now let's say that they give you a range. Okay. Mostly in questions, let's say you would be getting that, let's say that the voltage varies somewhere from 200 volts to 260 volts. Okay. Let's say I'm assuming stuff. Okay. So now the question is, would you design for 200 volts or 260 volts? That is the question, right? Do you understand? So over here in the question, they have given 230 volts. But let's say in your examination or anywhere else, you become an engineer, you want to design the inductor. And in that case, would you design for 200 volts or 260 volts? What is the worst case that you would consider? Normally, what you think that, okay, let's design for worst case. So let me take 260 volts. But no, you understand, right, that the peak current would appear only for the V minimum case. Okay. So you would design for 200 volt, not for 260 volt. Okay. Is this concept clear for you guys? What is the minimum I am referring to? Is this fine? So if you are having a range of input voltage, so over here in the question, they have given only one value, that is 230 volts. Okay. But let's say they give you a range. The input voltage can vary from 200 to 260 volts. Even in India, you see that it's not fixed at 230 volts. At some point of time, you will get 210 volts. At some point of time, you will see that there is a voltage sag. You get only even 205 or 200 or 195 volts. At some places, you get 230 volts properly and so on. So you would have to design your inductor not for the ideal rated condition. You would have to design for the worst case condition. Okay. So if they give you a range of input voltage, you have to know what voltage should be taken. Is this understood? I hope this is fine. If you are having a doubt, please type in the chat box. Anyway, so over here we are not having that headache. So right now we are having only 230 volts as the input. Okay. So okay. So anyway, our Vin is just a single number. Now the question is, should it be RMS value or the peak value? The point is, I have written what is IL peak. Okay. I peak value, correct? So again, this is your peak value. Okay. So you can write this um, sure. Yeah. Okay. So you can write this as root 2 into P naught divided by V in RMS. Is this fine? IL peak is root 2 into P naught by V in RMS. Okay.
Hello, sir.
Yeah.
Sir, I have one doubt. Is that during the DTS period, you wrote the equation Vs is equal to L di by dt, right?
Correct. Yeah. Go ahead.
Yes. So di value is already given 1.5 ampere. Then what is the point of doing IL? What is the point of finding out the value of IL peak?
No, I was trying to tell from a generic perspective. We can solve the question from here itself. That's not a problem. I was
Sir,
trying to
for
tell it
that
from
case, the power is not required, no?
for which case?
Suppose if we write the equation for the t on time, t on period, dts period, then Vx is equal to L di by dt, di value is already given, that is 1.5 ampere, then power value is not required now.
What would be your value of duty?
Due to we can find out 1 minus Vs sin omega t by V naught. That Vs sin omega
Correct.
t we have already know. That 325 volt and V naught value is already given, that is 400 volt. So duty is
Correct.
fine. We can find out from that equation also. Then what is the point of finding out? What is the point of giving the power value? What is the use?
Yeah, in this particular question, they have already given other stuff itself. So yeah, you are right in one sense that you can find out from that itself. Yeah, it's not a problem.
But sir, the value is not matching. I calculate in both ways that you have calculated the IL peak value. So when so I am you are calculating the IL peak value. So I am find so where you use that one like IL peak value?
Yeah. So coming to that, yeah.
Okay.
Just hang on.
Okay. Thank you.
Okay, sure. Okay, so we are dealing with we were at IL peak. We know what is the value for IL peak right now, correct? Right. So now the question is, how would you select your duty? So what is duty? Duty is basically 1 minus V in by V naught. We are talking about IL peak. All are at peak values. So 1 minus V in peak divided by V naught. Okay, not RMS over here. So this would be 1 minus root 2 into V in RMS divided by V naught. This is your duty. Okay, fine. So we will use our equation, that is we just saw in the previous slide also that VL on is L into delta I by T on. So Vm sin omega t is L into delta I by dTs. Okay, so VL on is L into delta I by dTs, right? So what this gives us is L is basically VL on is Vn. So Vn into D divided by delta I into Fs, correct? So Vn is what? Vn is Vm sin omega t. That is fine, but we are dealing with V in peak over here. Okay. So V in peak is what? V in peak is V in RMS into root 2 into the D that you would calculate over here divided by delta I into Fs. All right. So this would be your value for L. Okay. So V in RMS is 230 volts. So 230 root 2 into D we would calculate 1.5 is your delta I and Fs is 70 kilohertz. Okay. Okay. So what is your value for duty? So what is the value for duty? V in RMS is 230 into 1.414 divided by 400 volts. So 0.8135 minus 1. Yeah, so your duty is 0.187. Is this fine? Yeah, so I'm getting sorry. Yeah, so I'm getting 579 microhenries. Hmm? Okay. So we'll go to the next problem. The next problem is single phase full bridge diode rectifier with capacitor filter is fed from 230 volt 50 hertz main supply. 1 kilowatt load is connected to the output. It cannot take a voltage ripple of more than 10% of the peak value of the input. Calculate the smallest value of capacitance that should be used to meet the requirement. Okay, so this is a DBR rectifier. Okay, and you are having a capacitor filter over here, and then you've got a resistive load. Okay, so what they have given is that so what they have given is it's fed from a 230 volt 50 hertz supply. So the power level is 1 kilowatt, and delta V cannot be more than 10% of the input. So 0.1 into peak value of input is 230 root 2. Okay. So how would the voltage vary? Voltage would vary from 100% to 90%. Okay, that is how the voltage would fall, and again it would rise from 90 to 100. Okay, calculate the smallest value of capacitance to meet the requirement. Okay. Okay, so so now the point is, so how would your voltage vary? Voltage, because of the capacitor, you would understand that under steady state, the capacitor, when the voltage is input voltage is less, it would discharge from 100 to 90%, 100 to 50%, and then it would again charge up. I am drawing it in an exaggerated fashion just for the sake of our own understanding. Okay, so this is how the voltage would vary. Okay, fine. So now the point is peak value is VD max. That is your peak value or V peak, right? Or VC peak would be your V in peak. That is 230 root 2. And your VC minimum would be 90% of V in peak. That is 0.9 into 230. Okay. Okay. Fine. So now the point is, so you would have also learned in the lecture slides, but the point is your PC minimum can be written as VC peak into cos omega t. Okay. That is in this particular is PC. So your cos omega TC is VC min divided by VC peak. Okay. So your omega TC is cos inverse VC min divided by VC peak. So that is cos inverse. VC min is 0.9 and VC peak gets cancelled. So cos inverse 0.9 would be omega TC. Okay. So you can write that TC is going to be cos inverse 0.9 divided by omega. What is omega? Omega is 2 pi f. So 2 pi into 50 hertz. Correct? Omega is 2 pi f. Okay. So cos inverse 0.9. Mind you that it should be written in radians. So cos inverse 0.9 is 0.45 divided by 2 pi into 50. So it gives us 1.436 milliseconds. Okay. Okay. So this is our TC. This is the charging period for the capacitor. Okay. So let me take a new slide. So now the point is the capacitance value is going to be how much? 1 minus TC 40 by 2 into PL divided by 2 V naught into delta V naught into 1 by Fs. Okay. So what is the average voltage across a capacitor? What is V naught? V naught would so V naught is somewhere in between, right? That is, this is the average value for V naught. Okay. This is the average value for V naught. I'm going a little fast because we are a little out of time. So V naught is basically VC min plus VC max over 2. Just an average. Okay. So VC min is 0.9 V peak. VC max is V peak over 2. So you get 0.9 V peak by 2. Okay. So V peak is 230 root 2. So if we calculate, you get 1.9 into 230 root 2 by 2. You get 309 volts. Okay. So V naught is 309 volts. All right. And so V naught is 309. And you know what is delta V naught? You know what is DC. Yeah, so everything else is known. So your capacitance value would be 1 minus DC is 1.436 millisecond. And what is T by 2? Your T is 20 milliseconds, so T by 2 is 10 millisecond. So 10 milli get cancelled, and the power is given as 1 kilowatt divided by 2 into average value for V naught is 309 and delta V naught is 10%, correct? Yeah, so delta V naught is 10%. So 0.1 into 230. 0.1 into 230 root 2, okay? And into what is the switching frequency for the capacitor? The capacitor switches every line cycle, okay? So 0.1 into 230 into root 2 into 50, okay? Oh. So what you get is so you get 852 microfarad. All right. So this is the capacitance requirement with this condition, that is, you have a capacitor filter for a single phase full branch diode bridge rectifier. Okay. Just you calculate what is the time for which the capacitor charges and use it over here. Okay. I think you would have learned about all this formula already in your lecture slides. Okay. Okay, so we have seen one question on boost PFC, one question on capacitor filter, right? And we have seen these theoretical problems as well. Okay. Yeah. So one more numerical problem is question number 8. That is for the single phase boost PFC converter fed from a 50 Hz AC source, having a varying voltage from 200 to 250 volts. What will be the minimum value of duty ratio reached if the output voltage is kept at 400 volts? Okay. So yeah, I was mentioning just a while ago that your input voltage can vary from a minimum value to maximum value. Okay. So for inductor design, you understand you have to take the peak current, therefore you will take the minimum value in consideration. Okay. Anyway, so the question is, what will be the duty ratio? So P of T for a boost converter is simply 1 minus V in by V naught. So over here it's going to be 1 minus mod Vm sin omega t divided by V naught. Okay. So the question over here is, what is the minimum value of duty ratio? Okay. So to get minimum value of duty ratio, you have to use 1 minus V max, right? Correct. So if you subtract V max, then you would get the minimum value. So what is the V max? It should be the maximum value. Maximum means you should use the max that's given. Okay. So 1 minus 250 root 2 divided by 400. Just have the distinction as to where you should use the minimum value, where you should use the maximum value. Here you should use 250. Okay, not this. So 1 minus 250 root 2 by 400. So okay, so let's. So I'm getting 0.116. This is the minimum value of duty. Okay, the least minimum, the minimum it would go is 0.116, right? Okay. Okay, so The next question is very interesting. Okay, it's not a numerical question, but the question is the switches S1 and S4 are turned on at the same time. Okay, S1 and S4 are diagonals. S1 and S4 are turned on at the same time, and S2 and S3 are turned on at the same time for 1 minute D period. Okay, so complementary operation. Okay, so what will be the expression for duty ratio D for S1? Right? So this is the converter. So what will be the expression for duty ratio? S1 and S4 are turned on together. S2 and S3 are turned on together. As I was telling earlier, identify what is the charging path. There is a diode bridge rectifier, which means that the inductor current would flow like this. Okay, inductor current would flow like this. Okay, so L charging, what is the path? L discharging, what is the path? If you know what is this answer, what if you know this, you get what is the answer. Okay. Okay, so let me copy this. Okay. Okay, so what is the L charging path? So when the inductor charges, they have told that S1 and S4 are turned on. So your inductor current would flow through S4 back. Correct? This would be the L charging path. Okay. VL. So what would be VL? VL would be input is mod Vm sin omega t as usual, but the output is getting connected. I mean, to the negative side is getting connected to the output. Correct. So input is mod Vm sin omega t. The output side is directly getting connected to V naught. Okay. So this is VL on. That is mod Vm sin omega t minus V naught. Okay. Okay. Fine. So this is the L charging period. What about the L discharging period? So during the L discharging period, the inductor current has to remain same. S2 and S3 are getting turned on. Okay. So you just trace the path for inductor current. You can understand that it would move from here. S1 is not, S1 is off. So the current has to go like this, go through the load in the reverse direction. Correct? And it will come through S3 and back. Okay. We started off over here. It will go like this. Through S2, S3, and then back. Okay. So what is the voltage? At the input side, we are still having mod Vm sin omega t. But at the output side, what is happening? The negative terminal, it is getting connected to the negative V naught. It is getting connected to minus V naught. Correct? Okay. So what is VL now? So VL during off period is going to be mod Vm sin omega t minus of minus V naught. Okay. So in the earlier case, it was mod Vm sin omega t minus V naught, just the difference between two voltages. Over here, the difference is mod Vm sin omega t plus V naught. Okay, this is your VL off. right? So let me call this Vn minus V0. So here it is Vn plus V0. Okay. So this is during the 1 minus V period. So this is during 1 minus dTs period. And this is during the dTs period. Okay. So we will now apply the inductor flux balance principle. So, by inductor flux balance or volt second balance, what you see is VL on to T on plus VL off into T off is 0. Okay. So VL on is Vn minus V0 into dTs plus VL off is Vn plus V0 into 1 minus dTs. Okay. So Ts gets cancelled. You expand this simply. So you get dVn minus dV0 plus Vn plus V0 minus dVn minus dV0 is 0. Okay. So you cancel out the relevant terms. So dVn and minus dVn get cancelled. Yeah, just this one. So what you end up is minus dV0 plus Vn plus V0 minus dV0 equals 0. So V0 into 1 minus 2d plus Vn is 0. So you get a relationship that so V0 into 2d minus 1 is equal to Vn, correct? So V0 over Vn is going to be what? V0 over Vn is going to be 1 by 2d minus 1. Okay. Just flux balance principle, we are rearranging the terms, that's it. Okay. Or you write in terms of d from here itself. So we got minus 2d V0 plus V0 plus Vn equal to 0. So so 2d minus 1 is equal to Vn by V0. So 2d is equal to Vn by V0 plus 1. So d is equal to Vn by V0 plus 1 by 2. Okay. Yeah. So this is the answer, option D. Vn is Vs. So Vs by V0 plus 1 by. Okay. So is this question clear to all of you? All other numerical problems are just formula application based, but this one is, I hope this question is clear. Just apply inductor flux balance principle. Okay, great. So we will see the last question and we will break of the day. Okay, so the last question is straightforward. For the single phase boost PFC converter fitted up to 20 volts 50 Hz, if the duty ratio of the switch varies as shown below, what will be the output voltage rounded to 2 decimal points? Okay, so they have they have shown that T max is 0.95, D min is 0.15. Okay. The point is this question, this is for duty ratio of switch S1. Okay. What will be the output voltage? All right. So you take any one point and you find out. Okay. So correspondingly, if you draw the input voltage, right? So correspondingly, if you draw the input voltage, so your duty varies like this. How would your input voltage vary? Your input voltage varies like this. I'm sorry. So it varies something like this. Okay. So at the minimum value of duty, you get Vs peak. Okay. This is Vs peak. Okay. So at 0.15, what is the input voltage? Input voltage is peak voltage. Okay. Fine. So your input voltage is at its peak, right? So from this itself, you can find out. So V naught is what? So this is again a boost converter. So V naught would be 1 by 1 minus D times D in. Okay. That is 1 by 1 minus D min into V in would be peak value. Okay. That is Vs peak. Okay. So you directly substitute 1 by 1 minus 0.15 into D minus 0.15. V peak would be 220 to 2. To find out the answer. So answer is 1 minus 0.15 is okay. So this is 0.85 and so I'm getting 366 volts. They have told 2 decimal places, so 0.03. Okay. Is this fine? So just take the operating point and from that itself you can find out. Okay. Yeah, so this was a simple question. Okay, so yeah, so any doubts so far, or we will break for the day? For some questions like for which we were taking it offline, so I will solve those and upload it in the drive. I will update the drive PPT. Okay. For now, anyway, the PPT is there. You can refer to that, and I have also written just the answers below each slide, so you can refer to the answers also. So yeah, so thanks everyone for attending. We are past 8 anyway, but we faced a few issues. In the starting, it was due to my login issues, and later on, it became due to the screen not being visible. So in the next class, I will try to run some. Before coming, I will just try to check if it's fine with other laptops, because we cannot keep on facing this issue. Anyway, so thanks everyone for attending. So have a great week ahead, everyone. Yeah, thank you.